Well, in this discussion, we're going to talk about rational functions and their graphs, but we're really not talking here about graphing rational functions. We're more concerned with the introduction, and that's the features of the graphs of rational functions. So, of course, we start off with the idea of what is a rational function. Well, here are some examples of rational functions. And they're really fractions where the numerator and denominator are both polynomials. And you'll see in this very first function, the numerator is just the constant 1, but a constant can be thought of as a polynomial function. Usually we have something other than a constant in that position, as you can see in the other two examples, polynomial divided by polynomial, and so on. So rational functions are nothing more than fractions whose both numerator and denominator are, in fact, polynomials. Now, the simplest example of a rational function is the function f of x equal 1 over x. And we recognize that that function is defined for all values of x except 0, because 0 would cause the denominator to be 0, which is, of course, not allowed. If we were to begin to graph this, we would choose some x values, and I've put up a little table here. For instance, when x is equal to 1/2, then f of x, or y, would be 1 over 2. Excuse me, when x is equal to 2, pardon me, then f of x, or y, would be 1 over 2, and of course 1 over 2 can be thought of as the decimal 0.5. And as we look at these values of x, what's happening here is that x's are getting smaller but closer and closer to 0. These are all positive x values, but they're closer and closer to 0. And we recognize, remember, x is the denominator. And when the denominator gets very small, then the value of the fraction gets very large. And so that's what we're seeing. As the x's get closer and closer to 0, the y values get larger and larger and larger, and that's a big issue. Now, on the other hand, as the x's get bigger and bigger and bigger, as we see here, then that's the denominator getting bigger, and the bigger a denominator is, the smaller the fraction. So the fraction represents y, so we see the value of y is getting smaller and smaller and smaller. That is, it's getting closer and closer to 0. So the bigger x is, then the closer y is to 0, and that tells us quite a bit about what the graph of the function would look like. Because remember, as our x's were getting closer and closer to 0, that would be here, then our y's are getting larger and larger and larger. That's up here. And as our x's got bigger and bigger and bigger, then our y's got smaller but positive, so they got closer and closer to 0, and that's why the graph looks as it does in this case. Now, I only chose positive values of x, but although we can't choose x to be 0, we could choose negative values of x, and when we choose negative values of x, 1 over a negative number results in a negative number, so all of our y's are negative if we choose x's that are negative. And it gives us, we could go and analyze in a similar fashion. It would give us this part of the graph called the left branch. And of course, from previous things we've done in the course, we already have some idea, of what the function f of x equal 1 over x looks like. Now, keeping that in mind, we can, knowing what that looks like, we could create new functions and graph them using the concept of transformations. Let's see here. So if we look up above in our function here, if we didn't have this -1 and we didn't have this +3, what we would have is the graph of just 1 over x. But that -1 and +3 cause the graph to change. And remember, when we're subtracting or adding to x, as we've seen when we did with transformations, that causes a horizontal transformation. So that -1 causes a horizontal transformation, but that +3 causes a vertical transformation. Well, -1 horizontal transformation causes the graph to move right 1 unit, and +3 vertical transformation causes the graph to move up 3 units. So the idea is, if we start with the graph that we're familiar with, whoops, okay, that's the 1 over x. If we shift it to the right 1 unit, as that -1 would tell us to do, it would look like that. And then if we turn around and shift that graph up 3 units, then we would see that it would look like that. Now those red dashed lines we'll discuss a little later, but those are called asymptotes. The horizontal dashed line is a horizontal asymptote, and the vertical dashed line is a vertical asymptote, and we have a way of predicting where those will be. Now, finding x and y intercepts of rational functions is something that we want to do, but we're going to always want to assume that the rational, well, we better be careful about assuming, but we're always going to want to deal with a rational function that is in reduced form. So we're assuming that this function, which is polynomial p divided by polynomial q, is in reduced form or lowest form. That is, p and q have no common factors. To find the y-intercept, always remember how we find a y-intercept. Oh, well, when we have y-intercepts, it's the x value that's 0, so we substitute a 0 in for x and we calculate the y. Now, of course, if 0 gives us an invalid result, like gives us a denominator of 0, then the function has no y-intercept because x would have to be 0 and is not allowed. So we need to be a little bit, occasionally we don't have a y-intercept, and that is how we decide if y is not in the domain is by putting a 0, a 0 is not in the domain by substituting 0 for an x, and we would have an undefined result, that is a denominator of 0. Now to find the x-intercepts, we know that we must, that's when y is 0. So we substitute a 0 for y, as it says down here. So we substitute a 0 for y, f of x, and solve. And so we've got a fraction is equal to 0, and we solve that equation to find out what x has caused that to happen. And if the equation has no real solutions, as it says here, if it has no real solutions, then in that case, there are no x-intercepts, if there are no real solutions to that equation. Well, I'm having trouble getting that highlighted correctly. Okay. Well, all I want to do before we get too far into this is I just want to show you some examples first of rational functions. And at the bottom, of course, you can see the function itself. Let me get a pointer so I'm not messing this up. So at the bottom, we see the function itself, and of course, the graph is above it. Remember, these red dashed lines are not really part of the graph. They're guidelines that are called asymptotes. So this is a vertical asymptote. This is a horizontal asymptote. And in a few minutes, we'll be able to look at this function definition and decide what the asymptotes would have been. Now, here's the idea. A horizontal asymptote, the graph gets close to way out on the left and way out on the right, maybe not in the middle. And a vertical asymptote, as the graph approaches a vertical asymptote, it's either going to go way, way up or it's going to go way, way down. It won't cross a vertical asymptote. We'll see why in a moment. Okay, here's another example of a rational function, and you can see that it has 2 vertical asymptotes, and it's hard to tell right here, but there's a red dashed line on top of that x-axis, and that is the horizontal asymptote. And by the way, we can have several vertical asymptotes, but we can have no more than one horizontal asymptote. And notice here we have 3 different parts of the graph. Well, we have a part of the graph between and beyond vertical asymptotes. In other words, the vertical asymptotes break the the plane, if you will, into three separate parts, and we have a branch in each of those parts. Here we had one vertical asymptote, and we had a branch to the left of that and a branch to the right. Here we have two vertical asymptotes, a branch to the left of the furthest left, a branch between the asymptotes, and a branch to the right. Notice, although you might think that the horizontal asymptote breaks it into a top and a bottom, that's not the case. It just happened to be the case on this first one. But here you see that we have only one horizontal asymptote, but we have three parts to the graph. And it's the vertical asymptotes that determine how many parts to the graph. Well, once again, we see a graph here. One of the ideas that I hope that you're getting is these graphs can look wildly different. Here we have two vertical asymptotes once again and one horizontal asymptote. Since we have two vertical asymptotes, we would expect three branches, one more than the number of vertical asymptotes. Now, in this example, we only have a horizontal asymptote and we have no vertical asymptotes. And so there's only one branch, there's only one part of the graph. But once again, as we look at these, when we are going way out to the right and way out to the left, our graph is getting closer and closer to that horizontal asymptote. As we get close, the graph gets close to the vertical asymptotes, it's either going to shoot way up or it's going to shoot way down. It's going to shoot way down or it's going to shoot way up. And in this case, we don't have a vertical asymptote, so it doesn't shoot way up or down. But as we go way to the right or way to the left, the graph is getting close to that horizontal asymptote. Okay, well, here are a couple of stranger ones, and these are really just to kind of give us an idea once again. These red lines aren't dashed, but they're still asymptotes. Now, of course, there is a vertical asymptote. This case, there is no horizontal asymptote. See, there's no red dashed line. But there is this slanted asymptote that is also called an oblique asymptote. And what's happening is on the slanted asymptote, as we go further into the right, the graph is getting closer to that slanted line. As we go further to the left, the graph is getting closer to that slanted line. But once again, as the graph is approaching a vertical asymptote, the graph goes way up or the graph goes way down. And this example is a very exotic graph. In this case, there is a vertical asymptote that's hard to see, but it's the same as the y-axis. There's a red line on top of that y-axis. And so we have two branches, one on each side of the vertical asymptote, just as we did here. There is no horizontal asymptote. There's no slanted or oblique asymptote. There's this red dashed line that looks like a parabola, which is in fact what it is, and this is called a parabolic asymptote. So the further we go to the right, the closer this portion of the graph is getting to that parabolic asymptote. Further we go to the left, it's getting closer. But as we get close to the vertical asymptote, also the graph is shooting up in both cases on each side here. Now we can also have rational functions that have holes in them. And so you see here we have a vertical asymptote, a horizontal asymptote, and as we go to the left and go to the right, the graph's getting close to the horizontal asymptote. As we come close to the vertical asymptote, the graph is going up, the graph is going down, and you see right here there's actually a hole in the graph, and we'll find out how we can predict that as well. Okay, well, to find intercepts of a rational function, we first need to make sure that the rational function is in, oh, we've already talked about this, isn't it? It's got to be in lowest terms. I'm sorry, I've got a repeat here, so we'll move on. Now, how about finding the domain of a rational function? Well, the way we would find the domain, remember, a rational function's a polynomial divided by a polynomial. And so we would find the domain. The only place that type of fraction would be undefined is if the denominator of that fraction is undefined. So we look to see what causes the denominator to be undefined. And here we can see it would be undefined if x is -5. So it's the set of all numbers x except -5. And in set builder notation, this is the way we've written that in the past. set of all x's such that x is not equal to -5. Okay, let's consider the domain of 1 over x squared minus 4. Same idea. We've got to decide if there's any x values that would cause the denominator to be undefined, because those are the only x's that would be bad. And of course, if we have x squared minus 4, we know either a positive 2 or a negative 2 when squared would give us 4 minus 4. And so there would be two values of x that would cause that denominator to be 0. And so the domain of this rational function is the set of all x's, so that x is not -2, and also x cannot be equal to positive 2, but x can be any other values. Now look at the domain of this function. This is an interesting one. X cubed over x squared plus 1. Now, if we tried to find the values of x that make x squared plus 1 equal to 0, we would be trying to solve the equation. See, what would we end up doing? We'd be trying to solve the equation. Well, I apologize here. This isn't quite as smooth as I want it to be. But we'd be trying to solve the equation x squared plus 1 is equal to 0. Because we want to know what x has caused the denominator to be 0. And since the denominator is x squared plus 1, what causes that to be 0? Well, we could solve this by using a quadratic formula. We could also solve it by doing what we call extracting square roots. That is, separating the x squared from the constant. So we'd subtract 1 on both sides. But when we do that, we recognize x would be plus or minus the square root of -1. And of course, we remember that the square root of -1 is not a real number. In fact, the square root of -1 is the complex number I. And so there are no real values of x. There are no x values that are real numbers, no x values that we can plot that would cause the denominator to be 0. So in this case, the denominator is the domain is the set of all real numbers. And of course, we could write that in terms of an interval, -infinity to +infinity, if we so desired. Okay. Well, what about the domain of x squared minus 1 divided by x minus 1? Now, this is a little trickier, okay? Well, I say that. I guess it's not really very tricky here, is it? We can look at it, and I apologize. I was someplace else, I guess. What causes the denominator to be 0? Well, would be 1. And so this is going to be defined for any values of x except 1. And so the domain is a set of all x's such that x is not equal to -1. Okay. Now, sorry, let me get rid of stuff that I wrote down here so we can read this. This is going to be something that's kind of important for us later on, and it's certainly important in calculus. If we look at this function, it's not reduced. It's x squared minus 1 over x minus 1. Remember, x squared minus 1 could be written as, x squared minus 1 can be factored as x plus 1 times x minus 1. And if we did that, we would have this factor of x minus 1 in the numerator and this factor of x minus 1 in the denominator. And so in reduced form, r of x would be the same as the function f of x is equal to x plus 1, except in the very beginning, we already know that r of x is really defined this way, and x can't be equal to 1. So what we could say is that r of x is equal to x plus 1 provided we never let x be equal to negative, pardon me, yeah, x be equal to -1, because that was the issue in the very beginning, wasn't it? We, excuse me, +1, my bad, +1. Should have just not put that at all. Remember, because we knew in advance by looking at the function itself, since the denominator is x minus 1, we couldn't let x be 1 to begin with. As long as we don't let x be 1, then it's going to be in a reduced form the same value. Oops. Same value as x plus 1 would give us. So those two are equivalent, basically. Okay, finding vertical asymptotes. The idea is really simple behind a vertical asymptote. Vertical asymptote is a vertical line through any x values that are not in the domain of the function. And that means if they're not in the domain of the function, they're values of x that cause the denominator to be 0. So all we have to do is look at the denominator of the function, decide what x values cause it to be 0, and then we know that the vertical line through that value is a vertical asymptote. And vertical lines are given by the equation x equal. Remember, horizontal lines are y equal a constant. Vertical lines are x equal a constant. So as we look at this first function, we can predict that the vertical asymptote is going to be the vertical line through what? Well, what causes that denominator to be 0? A value of -3. So remember, this x equal -3 is representing a vertical line, not just a number. That's a vertical line. That's the vertical asymptote. Well, if we look at the next rational function, the denominator is already factored, and there's two values of x that cause the denominator to be 0. If we have an x value of -2, then this factor will be 0. If we have an x value of +2, then this factor will be 0. So there are two vertical asymptotes. There are two vertical lines, and they go through those two x values. So x equal 2 is a vertical line through 2, and x equal -2 is a vertical line through -2. So this function has two vertical asymptotes. Likewise here, we got a little more of an issue because we can't see the factored form of that denominator. It's not so obvious. But if we factor that denominator, so let's see, x squared plus 5x plus 4. Let's see if we factor that denominator, what would it look like? Well, how about a +4, ugly plus, and a +1. That has it factored, doesn't it? And of course, what causes this factor to be 0 is an x value of -4. So we have a vertical line through -4 given here. What causes this factor to be 0? Well, an x value of -1. And so that's where this other one comes from. So sometimes we have to do a little work. We can't just look at it and know what x values cause the denominator to be 0. But it's usually not too difficult. Well, this very last one, and once again, I've got things on top of others, so it's kind of hard to read. Remember, we just care about what causes the denominator to be 0 because that's where it's undefined. And so in this case, the denominator being x squared minus 4, we know if x is +2 or -2, then that denominator would be 0. Oh, but look here. There's an issue here. That says there's only one. That's a big deal. We were expecting 2, weren't we? This says there's only one vertical asymptote, and it's when x is equal to 2. Well, here's why. This function g is not in lowest terms. It's not reduced. See, if we go about and factor this numerator. Whoops. We factor this numerator, it will factor as x plus 2 times x plus 1. That's the factored form of that numerator. The factored form of this denominator, I don't have room below, so let me write it as x, whoops, plus 1 there. Somehow that didn't get in. So we have x plus 2 times x plus 2. Oh, goodness. Times x minus 2 as the factored form of the denominator. Well, the x plus 2's, when we reduce, we'll still have to remember that x can't be negative 2, but when we have this reduced, the denominator is x minus 2. And so what causes that denominator to be 0 is an x value of 2. So to determine, once again, to determine vertical asymptotes, the function, the rational function, has to be in reduced form before we can tell for sure what the vertical asymptotes are. This common factor in the numerator and denominator cause a hole. So I would expect a hole at the x value that causes that x plus 2 to be 0, and that's when x is negative 2. So this graph would actually have a hole in it and only one vertical asymptote. Okay, let's go through these graphs that we looked at before, and now we can make some sense out of what we've already seen. In this case, the denominator is x plus 1. Well, what causes that denominator to be 0 is an x value of negative 1. And you can see that our vertical asymptote goes through that x value of negative 1, and there it is. So that makes sense of what we've just been describing. Now, it might be worthwhile here. Let me erase that. It's pretty ugly, isn't it? It might be worthwhile here to understand why this is happening. Remember, when x is negative 1, the function is undefined because the denominator would be 0. And that's why we see that this graph is not ever going to go across that vertical line. But when x gets real close to negative 1, see, like if x was a negative 0.9, then this denominator would be very small, wouldn't it? And remember what happens. A very small denominator causes a very big fraction. Small denominators cause the fraction to be big, and the fraction is a y value. So a small denominator, that is when we get close to where the denominator is 0, when we get close to that, that means the denominator is a small number. And if the denominator is a small number, then the fraction, or the y value, will be a big number. Now sometimes that big number is positive, and sometimes that big number is negative. But that's why the graph shoots up or down when we get close to a place where the denominator is 0, close to a place. And that's why these vertical asymptotes exist. That's where the denominator is 0. We get close to those places, the fraction will be real large positive or real large negative. Now, when we look over here, of course, we can't tell right away what causes that denominator to be 0. And so we're forced to factor that denominator. So if we can here, we'll have an x, let's see here, times an x. And how about an x minus 2 times an x plus 1? Is that factored? I believe it is. So what causes x minus 2 to be 0 would be when x itself is 2. And if so, the vertical line through x equal 2, which is right here, okay, we would in fact expect that vertical asymptote to exist. Now here in this factor, what causes this factor to be 0 is when x is negative 1. And so if we look at the vertical line through x equal negative 1, we have the other vertical asymptote. So very easy to do, actually, isn't it? Sometimes we just have to do a little factoring to predict it. Oh, I forgot that I already had that in factored form there. Well, when we look at this one on the left, okay, when we look at this one on the left, when we look at this denominator, x squared minus 1, well, there are two x values. There's no factors in common. All of these are reduced. And there's two x values that cause x squared minus 1 to be 0, if x is positive 1 or if x is negative 1. So we have two vertical asymptotes, the vertical line through x equal positive 1 and the vertical line through x equal negative 1. Now, on the other hand, if we look at this particular denominator, we saw this idea previously. There's no real numbers for which x squared plus 1 will be 0. Because we take a real number and we square it, we get a positive number, or the very least would get a 0 if we squared 0. So x squared plus 1 is always going to be 1 or bigger, so there's no way it will ever be 0, so there's no denominator that's ever 0, so there's no vertical asymptote. Well, in this case, in the fraction on the left, the denominator is x minus 2. What causes that to be 0 is x equal positive 2. So you see at x equal positive 2, we have a vertical line through that x equal positive 2, which is the vertical asymptote. Down here, we see x squared as the denominator. The only way x squared will be 0 if it's x itself is 0. And so we have a vertical line through x equals 0 as the vertical asymptote. It's really very simple, isn't it? Well, finding horizontal asymptotes is a little more of an issue. A little more of an issue. Hold on here. Well, I apologize for that. Okay. It's a little more of an issue, but it's still not difficult. Now, there's an awful lot of stuff that we see overhead. It says finding horizontal asymptotes or oblique, which is the same as slanted asymptotes. First, we're going to concentrate on finding horizontal asymptotes. Now, this is just to illustrate, and I want you to recognize that we have a polynomial divided by a polynomial. Well, a polynomial is going to be constants times x to powers. And we're going to assume that this is the largest power of the numerator is n. So the degree of the numerator is n. And this just represents the coefficient of x to the nth power. And so that's the leading coefficient of the numerator. On the other hand, the denominator has a degree of m. We're assuming that's the largest power of x. And so the leading coefficient then would be this, whatever this number b subscript m is. That's the leading coefficient of the denominator. Now, here's the issues, and we'll see examples of this, but right now I'm just going to talk about it. If n, that's the degree of the numerator right up here, is the same as m, that's the degree of the denominator. That is, if the degree of the numerator and denominator are the same, then the horizontal asymptote is the line y equal, remember it's a horizontal line, and horizontal lines are given by y equal a constant. Well, it's y equal the leading coefficient of the numerator divided by the leading coefficient of the denominator. So all we do is look at this leading coefficient on top and this leading coefficient on bottom, and y equal to that ratio is the horizontal asymptote. But that's only if the two degrees of the numerator and denominator are the same. Now, if the degree of the numerator, which is n, is smaller than the degree of the denominator, so that means the degree on top is smaller than the degree on bottom, then the horizontal asymptote is simply the line y equals 0. And the line y equals 0 is the same as the x-axis. So if the degree on top is smaller than the degree on bottom, the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote will simply be y equals 0, the x-axis. Now here we have the degrees the same, number one. Number two is the degree of the numerator smaller than the degree on the denominator. The only other possibility is if the degree of the numerator is bigger than the degree of the denominator. Now, in general, if it's bigger, and I should really write it this way. Let me point this out. If we actually had the degree of the numerator simply bigger than the degree of the denominator, that's supposed to be a greater than, then there is no horizontal asymptote. But if in fact, as I've written here, if the degree of the numerator is exactly one more than the degree of the denominator, that's what that says. The degree of the numerator is exactly one more than the degree of the denominator, then we have a slant asymptote. And the slant asymptote is the line y equal to, this looks like a line, doesn't it? Constant times x plus a constant. Usually we call that a, m for the slope, don't we? But this ax plus b, how do we find that? Well, what we do is we divide the denominator into the numerator. Remember, the denominator has a smaller degree than the numerator. And so it will divide into it. And when we divide into it, then we'll get a quotient. And that quotient is represented by ax plus b. So it will be y equal to that quotient. We ignore the remainder when we do the division. It's only y equal to the quotient. And we'll see some examples of that later. Now, the graph, as it notes down here, the graph in a rational function either has one horizontal asymptote or one oblique asymptote, or else it has no horizontal or no oblique. You can't have one of each. It's one or the other or none. Okay. Now, look at this first function. The degree of the numerator is the power of x there, which is 1. And the degree of the denominator is the power x here, which is 1. So the degrees are the same. Well, remember, when the degrees are the same, then the horizontal asymptote is given by the line y equal leading coefficient divided by leading coefficient. Well, the leading coefficient of the numerator is a 2, and the leading coefficient of the denominator is a 1. So it's the line y equal 2. Well, sure enough, if you look above, that's exactly what we've got, isn't it? Here's where y is equal to 2, and the horizontal line through that line, you can see, represents the horizontal asymptote. Now, in this second example, on the right, the degree of the numerator is 1, but the degree of the denominator is 2. And remember, if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is given by y equals 0, which is nothing more than the x-axis. And you can barely see it there, but you can see that that's what I've drawn in above. Y equals 0 is that dashed horizontal line right there. And of course, we recognized before that that was a horizontal asymptote. Now, when we look at this next example, on the left, f of x equal 2x squared over x squared minus 1. The degree of numerator and denominator are both 2. So when the degrees are the same, it's y equal leading coefficient over leading coefficient, or y equal 2. That's just a coincidence to what we had a while ago, but certainly just y equal 2. And you can see that the horizontal line y equal 2 is represented on this graph as the horizontal asymptote. And when we look at the one on the right, we first might be stumped. What's the degree of a constant? What's the degree of a constant? I can't find my pen. I'm sorry. Okay. I come down here. What's the degree of this constant? Well, the degree of that 4, remember we talked about this previously, the degree of a constant is 0. And the degree down here is 2. And so, whoops, 2. It's supposed to be a 2. And at the bottom of my page, and so, okay, 2. So when the degree of the numerator is smaller than the degree of the denominator, once again, the horizontal asymptote is simply the line y equals 0, which is the x-axis, and that's what we see happening there. Okay, now in this next example, we notice that the degree of the numerator is 2, but the degree of the denominator is 1. Okay, and so the degree of the numerator being exactly 1 more than the degree of the denominator means we have an oblique or slanted asymptote, as we see here. Now, how do we find that slanted asymptote? Remember what we do. We take the denominator and divide it into the numerator. And so that's what I've shown here. And when we do that, and you can read through that as you will, we ignore, I knew I was finished with the division because I've got a remainder that's constant, so x minus 2 won't go into 4 anymore. But what we do is we set y equal to the quotient when we're finished doing that dividing, and that's what I've done here. Y equal to x. See, that's the quotient above. The 4, don't worry about. Don't worry about that. So y equal x is this slanted line that we see over here. Again, I keep running off where I can't find my pointer. Way up here. So that slanted line, that oblique asymptote, or slanted asymptote, is the line y equal x. Okay, here we have, let's talk about this function real quickly. If we looked at the function, let's see, here's the function that's what we see the graph of. We would think that there is a slanted asymptote because it appears the degree is 2 for the numerator and 1 for the denominator. Degree on top is exactly 1 more than the degree on bottom. But the fallacy here is, for any of this to work, the function has to be in reduced form. And 2x squared plus x minus 1 divided by x plus 1 is not in reduced form. You see when we factor 2x squared plus x minus 1, we get 2x minus 1 divided by x plus 1. And so when we cancel those x plus 1s, we just simply get f of x is 2x minus 1, which would be a straight line. The only issue is because the denominator of the original function was x plus 1, we knew we would never be allowed to let the x be negative 1, and that's why we have this condition out here to the side. From the very beginning, x couldn't be negative 1. Well, here is where x is negative 1, and that's where the hole is. So it's a line except for that value where x is negative 1. So it's critical to have this thing in reduced form before we do any analysis whatsoever. Now here's another example of a rational function with a hole in it. You already see the graph. If we were not careful, we would think that we would have 2 vertical asymptotes. And we saw this before. And you might be able to say, oh, well, some of this stuff looks like it's okay, but we really are ahead of the game. See, we would look at this and we might think that there are 2 places where this denominator is 0, so we would expect 2 vertical asymptotes, but you see we only have 1, and we have a hole in the other place. So here's the issue once again. We assumed that it was reduced, and we shouldn't do that. If we factor the numerator denominator as I have here, you see that we have a common factor, and that common factor can be canceled. But of course, from the very beginning, x can't be equal to 2. See, x couldn't be equal to 2, and we have to keep that in mind from the original definition of the function. So the graph is going to look like f of x equal 2x minus 1 over x plus 2, except that we can't let x be equal to 2. And when we look at this graph, then because of this denominator, we expect a vertical asymptote at x equal negative 2, and you can see that we have that. and the degree of the numerator is 1, and the degree of the denominator is 1, and so the horizontal asymptote is y equal to leading coefficient 2 over leading coefficient 1, which is 2. And you see we have that horizontal asymptote. But since x can't be equal to positive 2, which is right here, then that's the place on the graph that we have a hole. Well, that finishes my discussion here on rational functions, and so, or at least the pieces of rational functions, analyzing them. And in the next lesson, we'll talk about actually graphing.